A central notion in probability theory is conditional probability and independent events. To discuss them, let us consider a real-life example. Assume you run an online shop and you have some client and you know nothing about your client when they just came to your shop, just open your website. But if you see that this person adds some dog food to their cart, you can assume that this person probably has dog. And it means that it is a good idea to recommend them some other stuff that can be interested for dog owners. For example, some toy for their dog. This is simple reasoning, but we can formalize it using notion of conditional probability. Let us consider a random experiment when we pick a random person from a set of all potential customers. Then we can consider event A, that this person wants to buy dog food. Because the person was chosen randomly, this is a random event. And we can also consider another random event, that this person wants to buy a dog toy. Then we can assume that every 10th client buys dog toys. So it means that probability of B is 1/10. However, if we see that a particular person already added some dog food to their cart, we understand that event A occurred, and we can suggest that the probability of B is much larger than 1/10 in this case. Thus, events A and B are not independent, because conditional probability of event B, provided that A occurred, is larger than probability of event B. In this way, we can use our knowledge of event A to make some predictions about event B. This is basically how supervised learning works. In supervised learning, we find some dependencies in the data and predict something that we don't know using the information that we know. What will we discuss at this lecture? First of all, we discuss notion of conditional probability that formalizes the idea of dependency between events. We also study notion of independent events. We will study how to test for independence and how to use it. And finally, we will apply our notion of conditional probabilities. We will study law of total probability and Bayes rule. In supervised machine learning, we are building predictive models that predict value of some variable using values of some other variables. This is possible if there is some connections between these variables. To study this kind of connections, we have to study conditional probabilities and the notion of independence of events. Let us begin with example. Let us assume that we are performing a study that is interested in how marriage is related to happiness. To perform this study, we conducted some survey, and now we have some data set which contains information about is a particular participant married, and is he or she happy. So we have a table that can look like the following. Here is participant ID, Here is married, and here is happy. And we have some answers here. For example, participant number 1 is married but not happy, and participant number 2 is married and happy, and participant number 3 is not married but also happy, and so on. It is possible that we have a lot of participants. And what we are interested in is are there any connection between the value of this variable, is a particular participant married, and this variable, is he or she happy. For example, we are interested in the probability to meet a happy person, depending on the fact is he or she married or not. To ease the processing of this data, let us consider the following new table, which is constructed using this table. This is called a contingency table, and it is constructed in the following way. We have two variables, happy and married. The values of happy are yes and no, and the values of married are also yes and no. And let us put some numbers here. For example, let us assume that in our study we have 42 participants who are happy and married. So in this table we have 42 rows for which we have yes, yes. And the rest of values are shown here. In this case, we can find that overall number of married participants is 70, and overall number of not married participants is 30, and we can also find overall number of happy participants, which is 48, and overall number of non-happy participants, which is 52. Now let us consider the following random experiment. We pick random participant from our study, or you can think about this table. We pick a random row of this table. We will use equal probabilities for each participant. Now the set of all outcomes is the same as the set of all participants. The number of outcomes equals to the overall number of participants, which is 100. You can find by summation of these numbers. Now, as we defined probability space, we can ask probabilistic questions, questions about different events. For example, we can consider event which is called H, and it means that the chosen participant is happy. And we can also consider event M, that is, the chosen participant is married. Now we can find probabilities of some events. For example, what is probability of H? We see that we have 48 happy participants out of 100. So this is a 48 over 100. This is 0.48. In the same way, we can find probability that chosen random person is married. What is the probability of M? This is 70 over 100, which is 0.7. Now, let me ask. Assume that I know that a chosen person is married. For example, I see a wedding ring on this person. What can I say now about the probability that this person is happy? If I don't know anything about is this person married or not, then this probability is equal to 48 over 100. But if I know that the person is married, does it give me any new information about probability of H? You can look at this table and try to guess. But also we can just calculate. If we already know that the person that we chose is married, it means that it is one of these 70 persons with equal probabilities, because there is no any reasons to assume that one person from this set is chosen with higher probability than another person. So, probability that person is happy our randomly chosen participant is happy, provided that this person is married, can be found in the following way. We are interested in these 42 happy married persons. Out of these 70 persons. And this is equal to 0.6. Now we see that this probability is higher than probability that person is happy. This is different probability. It is denoted by the following symbol. This is probability of H under condition of M. This thing is called conditional probability. Here is vertical bar or pipe. Now we see that this probability equals to 0.6. Can you find probability that some person is happy under assumption that this person is not married. In this case, if we know that the person is not married, so the event M did not occur, it means that we choose our participant among these 30 non-married participants. And the corresponding probability, this conditional probability, is equals to 6/30. So, we see that if we know that person is married, we can predict, for example, in some machine learning prediction model, that this person is happy with probability 0.6, which is larger than the probability that this person is happy if we don't know anything about is he or she married or not. So we see that in this case, knowledge of one variable, of variable married, gives us some information about another variable happy. This kind of connections between variables is a key reason why machine learning algorithms can work. Now, let us study conditional probabilities systematically. Now, let us give a mathematical definition of conditional probability. Let us assume that we have two events, A and B. So we have some probability space omega. Let us assume that in this probability space, all outcomes have the same probability. This is for simplicity. Then conditional probability of A, provided that B happened, is equal to the following thing. We now consider only outcomes that are included into B. And out of these outcomes, we are interested in those who are also included in A. And now we think that B is a kind of new probability space. So we put number of elements in B in the denominator, and in the numerator we put number of elements that are in A and in B. So we put here number of elements in their intersection. This can be considered as definition of this conditional probability, and this is in agreement with the example that we discussed previously. However, to consider more complex probability space, we have to introduce a new definition. To do so, let us divide both numerator and denominator of this fraction by the same value, the number of elements in all probability space omega. The value of this fraction does not change. But now you see that in the numerator, we have probability of this intersection. And in the denominator, we have probability of B. So we can rewrite this definition in the following way. This is a probability of intersection A and B over probability of B. These formula give the same results. These two formulas give the same results in case when all outcomes have equal probabilities. But for different probability space, for example, for probability space where different outcomes have different probabilities, or in more complex probability space with infinite number of outcomes, this definition cannot be applied. However, this definition works as well. So finally, we define probability of A under condition of B as this thing. Note that this fraction is defined only if probability of B is non-zero. This is the definition of conditional probability. We can immediately make a corollary from this definition. If we multiply both sides of this equation by P of B, we have the following. Probability of intersection of two events equals to probability of A with by probability of B. This formula takes place. And this is a very important formula. We can interpret it in the following way. Let us think about this intersection. If this intersection occur, it means that occurred both B and A. Let us think about B first. B can either occur or not occur. And with probability P of B, B occurs. And with probability 1 minus P of B occurs not B. But this part is not interesting for us. This part is interesting. Now, if we know that B occurred, we can ask, what is the probability that A occurred? If we already know that B occurred, here we have to write probability of A under condition of B, probability of A given B. And here we have A intersection B. So to get here, the following things should happen. First, B should occur. Then, under condition that B occurred, A should occur. In this and only in this case, we are here, we are in this intersection. So, it is quite clear that the probability of this intersection equals to P of B times this conditional probability, which is given by this formula. The notion of conditional probability is very important. It allows us to discuss how one event affects another event. It also allows us to consider a case when two events are independent of each other. To discuss it in details, let us define the notion of independence. It is possible that two events are independent. It means that if we know that one event occurred, it gives us no new information about the probability of the other event. Let us consider example. Let us consider a study like we discussed before when we discussed marriage and happiness. But now we are interested in relation between some other factors. For example, we are interested in is it true that a particular participant likes cheese, or does he or she have dog? So it is possible that we have the following results of our study. Assume that we have 88 participants who has dog and like cheese, and we have 32 participants who don't have dogs but like cheese, and we have 12 participants here and 8 participants here. In total, we have 80 participants who likes cheese and 20 participants who don't like cheese, and we have 60 participants with dog and 40 participants without dog. Let us again consider a random experiment that we choose random participant of this study. And we have two events. C is event that occur when the chosen participant likes cheese. And D, chosen participant has dog. Let us assume that I'm interested in this event, in event C. I'm interested in, is it true that a particular chosen person likes cheese? I want to predict this, and what I know is, does this event occur? So is it true that the chosen participant has dog? Does this give me any new information about this event, event C? Let us calculate. So we are interested in conditional probability of C given D. As we discussed previously, this conditional probability can be found in the following way. We have to consider all participants with dogs, so this 60 persons, and this is in the denominator. And out of these 60 persons, we are interested in those who likes cheese. This is this number. We see that this conditional probability equals to 0.8. However, does it give us any new information about probability of C? Let us check what is the probability of C without any conditions. To find this probability, we have to consider all participants of our study. And we know that we have 100 participants of this study because this 100 is a sum of these two numbers or a sum of these two numbers. To find this probability of C, we have to divide these 80 cheese lovers over these 100 participants. So we have this value. And this value again equals to 0.8. So in this case, we see that probability of C under condition of D equals to probability of C. We see from this relation that if we know that some particular person has dog, it does not give us any new information about the preferences of this person regarding cheese. This probability is the same as this probability. It means that if we are interested in predicting of cheese, presence or absence of dog does not give us any new clues, so we can safely ignore it in our analysis. In this case, we say that C and D are independent events. The notion of independence is very important. Let us define it mathematically. Now we are ready to discuss a general definition of independent events. Let A and B be two events and let us assume that probability of both of them is non-zero. We will call these events independent if one of the following condition holds. First, we can say that conditional probability of A given B equals to just simple probability of A. Second, we can swap these events and replace here A for B. And third condition, intersection of A and B has probability which is equals to probability of A times probability of B. In fact, all three conditions are equivalent to each other. It means that, for example, if condition 1 satisfied, then condition 2 satisfied as well. Let us prove it. It is easier first to prove that condition 1 is equivalent to condition 3. Let us first prove that if condition 1 satisfied, then condition 3 is also satisfied. Let us recall the definition of conditional probability. So conditional probability of A given B equals to this ratio. Now let us use condition number 1, and we say that this probability equals to probability of A. Now let us look at this equality. We can multiply both parts of this equality by P of B. So this P of B goes here, and we have probability of intersection equals to product of probabilities. This is exactly third condition. We can go through this sequence of equalities in the other direction, because we can divide both parts of this equality by P of B and get this thing. So we see that from 3 it follows 1 as well. So condition 1 and condition 3 are equivalent to each other. In the same way, we can show that condition 2 and condition 3 are also equivalent, because condition 3 does not change when we swap A and B. Both parts of it consist of commutative operation over A and B. So we see that 1 is equivalent to 3 and 2 is equivalent to 3, and it means that 1 is equivalent to 2. So all these conditions are equivalent to each other, and we can use any of them as a definition of independent events. Now let us consider example and test, is it true that two given events are independent or not. Let us assume random experiment, which is dice tossing. Let A be event that number that we get is even, and let event B be that number is greater than or equal to 4, and let C be number is equal to or greater than 5. Which of these events are independent? Let us check. Let us first consider A and B. Which outcomes satisfy A? We have 3 outcomes: 2, 4, 6. And for B, we have also 3 outcomes: 4, 5, 6. Let us check any of these conditions. To do so, in any case, we have to find intersection of A and B. Intersection of A and B consists of the outcomes which belongs to both A and B. So these outcomes are 4 and 6. Now we have to find probabilities of A, B, and their intersection. Probability of A equals to number of outcomes in A divided by number of all possible outcomes, which is 6. So this is 3 over 6, this is 1/2. The same holds for B. Now let us look at their intersection. Probability of A intersects B equals to 2 over 6, which is 1/3. Let us check the third condition. If this condition is satisfied, this number should be a product of this number and this number. Unfortunately, in this case, this is not true. We see that this 1/3 is not equal to 1/4. So, A and B are not independent. We can think about it in a different way. If we know nothing, we can say that probability of B is 1/2, because we have 3 outcomes out of 6. But if we know that A occurred, then we know that one of these 3 outcomes occurred. And out of these 3 outcomes, 2 outcomes are in B. So it means that if we know that A occurred, it increases our expected probability of B. We can write it in the following way. Conditional probability of B given A equals to 2 outcomes here, this and this, out of 3 outcomes here. And it is not equal to probability of B. In other words, knowledge that A occurred changes the probability of B in this way. Now let us consider A and C. Are they independent or not? Let us check. First of all, let us enumerate outcomes that belongs to C. We have 2 outcomes, 5 and 6. Now we have to find intersection of A and C. A and C. Here we have only one common outcome, only 6. Now let us pass to probabilities. Probability of C equals to 2/6, 1/3. Now let's find probability of intersection of A and C. It is 1/6 because we have only one outcome. We see that this probability equals to product of this probability, P of C, and this probability, P of A. It follows immediately that A and C are independent. Now, I leave it as an exercise to consider B and C and answer the question, is it true that B and C are independent or not? It can be a little bit difficult to follow formulas. So, let us introduce some way to visualize conditional probabilities and check for independence of events. Let us recall our example that we discussed at the beginning of today's lectures. We discussed happy and married participants of some study and used this table to find some conditional probabilities. Let me show you how can we visualize this table. First of all, let us consider event M, that some person is married. Let me denote the whole probability space by some rectangle. We'll assume that both sides of this rectangle have length 1. Now, let me visualize the event M on this rectangle. We know that probability of M equals to O.7. So, let me pick a segment of length O.7, for example here, and the length of this segment is O.3. And now I draw a rectangle, and I say that this rectangle represents event M. And this rectangle represents an event that M did not occur, not M. We see that the area of rectangle is equal to the corresponding probability of corresponding event. Now, let us think about a second event that a chosen person is happy. I will draw this event as a union of two smaller events. First of all, let us consider event H intersect M. We know that probability that some person is happy, provided that this person is married, is equal to the following thing. We have to divide this 42 by this 70 and get O.6. So, we know that out of these married persons, 60% are happy. So, let me split this rectangle into two parts in the following way. I get here a segment of length of O.6 and consider this rectangle. This rectangle represents the following event. It represents the event that the chosen person is married because it is inside of this rectangle, and also the chosen person is happy because this married person is inside of these 60% of happy married people. So this smaller rectangle is happy intersects married. We can do the same thing with the other part. How many people who are not married but also happy? We can find the corresponding conditional probability. This is 6/30. So we have to divide this thing by this thing. And this is O.2. So I have to consider a rectangle which area is 20% of area of this rectangle. And this is intersection H intersected not M. Now, let us unite these two parts. this is H intersection with M, and this is H intersection with not M. If we unite them, we will get all happy participants. This is H. This diagram allows us to see conditional probabilities. For example, we immediately see that among married people, we have more happy people than among not married. It also gives us illustration to formula that we discussed before, that probability of intersection of two events, for example, H intersects with M, equals to probability of M times conditional probability of H under condition of M. Indeed, this probability corresponds to the area of this rectangle, and the area of this rectangle is a product of two numbers of the length of its sides. One side is O.7, which is probability of M, and the other side is O.6, which is conditional probability of H provided M. Now let us do the same thing and draw a similar picture for the second example that we consider. Example about the other properties of participants of our study. One property is that a particular participant has dog, and another property is that the participant likes cheese. So now we have two events, C and D. C likes cheese, and D has dog. And I'd like to visualize these two events in the same way. Again, I begin with a unit square. Let us begin with event D. Probability of D equals to O.6. So I put O.6 here. And this is D. And this is not D. So this rectangle represents those people who have dogs, and this rectangle represents those people who don't have dogs. Now let us consider cheese lovers, event C. Now let us find conditional probability of C provided D. It equals to 48/60, which is equal to O.8. So I put here a point O.8 and consider this rectangle. For conditional probability of C provided that not D, it equals to 32/40, and it again is equal to O.8. So this is C and D, and this is C and not D. On this picture, we see that the event C is uniformly distributed in a sense between D and not D. So we see that the conditional probability here is the same as conditional probability here, and it equals to just a simple probability of C, because here conditional probability is ratio of this thing and this thing, and this ratio is the same as the ratio of this thing and this thing. This picture represents independent events. We can say that this is C. And now you have some visual representation of independent and not independent events. We will use this representation when we will discuss law of total probability and Bayes rule. Sometimes we can check, is it true that two events are independent by calculating some probabilities? But more often, we can assume that some events are independent from some general considerations and use this knowledge to find some probabilities. Let us consider an example. Let us consider a professor who is going to the lecture. To go there, he have to drive through the city, and it is possible to stuck in traffic if there will be traffic jam. To avoid traffic jams, professor decides to depart earlier, and so he has to set up some alarm clock. Unfortunately, alarm clock can fail. We want to find the probability with which professor have to cancel their class. So, we have two events. Events A. Alarm clock failed. And event T. Traffic jam occurred. Even if alarm clock failed, if no traffic jam occurred, everything is fine, and professor will be on time at their lecture. But if both of these events occur, alarm clock failed and traffic jam occurred, then unfortunately professor have to cancel the class. So we have event C, class cancelled. Now we can say that C is an intersection of A and T. C occurs only if A and T occur simultaneously. Assume that we know that P of A equals to O.1. 1 over 10 times alarm clock fails. And assume that probability of traffic jam equals to O.3. It means that approximately 3 out of 10 days we have traffic jam. And we are interested in the probability of C. It is clear that professor's alarm clock does not change the probability of traffic jam. It is completely independent things. In the same way, it is clear that traffic jam does not affect professor's alarm clock. And so it doesn't change the probability of alarm clock to fail. It means that in this case, from our understanding of the world, we can safely assume that A and T are independent events. We can use these assumptions to find probability of C. In this case, probability of C, which is equal to probability of their intersection equals to product of probabilities, which is one of the definitions of independence. Then we can find it. We see that probability that a professor have to cancel their class is rather small. It is 0.03. Let us consider a different example. Let us assume that we are a company that have to make some decision. For example, to buy or not to buy some startup. To make this decision, a company can ask expert, is it a good idea to buy this startup? Unfortunately, every expert can be wrong. How can the company can decrease the probability that expert gives wrong advice? For example, company can ask several experts. Let us denote by E1 the event that the first expert is wrong. In the same way, denote by E2 the event that second expert is wrong. Let us assume that we are in a lucky situation when both experts agree in their recommendations. Then they can be either both wrong or both right. So, we are interested in the fact that they are both wrong, which is denoted by this intersection. What can we say about the probability of this event? It depends on the procedure of decision making. Let us first assume that these two experts make their decision independently to each others. It means that E1 and E2 are independent events. In this case, probability that they are both wrong equals to product of probabilities E1 and E2. Of course, we assume that these probabilities are less than 1. No expert will give us wrong answers every time. In this case, this product is less than any of these factors. For example, it is less than probability of E1. So, if both experts give the same advice, the probability that they both wrong is less than probability that only the first expert wrong. So, in a sense, in this case, committee of two experts is better than just one expert in terms of the error of mistake. However, it is also possible that the decisions of these experts are not independent to each other. For example, it is possible, it is in a sense extreme case of dependence, when the second expert just copy the solution of the first expert. In this case, they are both wrong or both right at the same time. It means that event E1 equals to event E2. Now, if we find the probability of their intersection, it is the same as probability of E1 intersected with E1, and this intersection is just event E1. So, we see that in this case, using of the second expert gives us no new information, and the probability of mistake is the same. Of course, these are two extreme cases, when both experts are independent and when they just copy each other's solution. In real situation, it is possible that there is some dependence between their actions, but it is not this full dependence as here. In any case, the more independent their solutions, the better from the point of view of this probability. In fact, we use the same idea in machine learning. If we have several predictive models that make independent predictions, we can unite these models and create a new model which is called ensemble. If our models behave more or less independently to each other, the performance of ensemble will be better than performance of one model. So far, we discussed notion of independence for two events. However, when we have three or more events, things becomes a little bit more difficult, and we have different notions of independence in this case. Let us discuss them. As usual, let us begin with example. Let us assume that we toss a coin 3 times. And we assume that it is a fair coin, so probability of head and tail is equal to 1/2. How many outcomes we have in this experiment? It is 2 to the power 3, which equals to 8. Example of outcome is head, 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 or head, head, tail. Now, let us denote by RG the result of G's tossing. It can be either head or tail. And let us introduce 3 events. A. It is event that R1 equals to R2, which means that the result of the first tossing is the same as the result of the second tossing. So we had head, head, or tail, tail. B is R2 equals R3, and C is R1 equals to R3. Now let us test, is it true that, for example, A and B are independent? To do so, as usual, we have to find probability of A, probability of B, and probability of their intersection. By the way, what is probability of A? Let us find it. Probability of A equals to probability of the event that consists of the following outcomes. If A occurred, then the result of first 2 tossings is the same. So we have head, head, tail, head, 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 tail, 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 head. We have 4 outcomes that corresponds to this event, out of 8 out of 8 outcomes. So the probability equals to 4/8, and it is 1/2. In a similar way, we can show that probability of B equals to 1/2 as well. Now, to test is it true that A and B are independent, we have to find probability of their intersection. If both events A and B occur, it means that the result of the first tossing is the same as the result of the second tossing, and the result of the second tossing is the same as result of the third tossing. It means that we have only two outcomes. Either it is head, 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 or tail, tail, tail. The probability equals to 2/8, which is 1/4. Is it true that A and B are independent? We see that probability of intersection equals to product of probability of A and probability of B. It means that A and B are independent. In the same way, we can show that A and C are also independent, as well as B and C. I leave it as an exercise. However, we can consider a formula like this one, but for 3 events. Let us check, is it true that probability of intersection of all 3 events equals to probability of A times probability of B times probability of C? To answer this question, let us consider this intersection. Note that if A and B occurred simultaneously, it means that R1 equals to R2 and R2 equals to R3. It follows automatically that R1 equals to R3, which is event C. It means that if we have all 3 events occur simultaneously, it is the same as only first 2 events occur simultaneously. So we have that this thing is equal to A intersection with B. Now we can say that this probability equals to probability of A intersection with B, and as we discussed before, this equals to probability of A times probability of B, and it is 1/4. Unfortunately, all 3 factors here are equal to 1/2. So this product is 1/8. We see that the answer to this question is no. We can interpret this result as a kind of dependence between C and both events A and B. In this example, we have so-called pairwise independence, meaning that all these 3 events pairwisely independent, A independent of C, B independent of C, A independent of B. But if we consider all 3 events as a system, we see some dependencies between them. In this case, this dependence can be understood as the fact that if A and B occurred, then C occurred with probability 1. In this case, we say that we don't have mutual independence between these three events. Let us give a definition. If we have three events, A1, A2, and A3, they are mutually independent. If, first, they are pairwise independent. It means that probability of intersections like this equals to product of probabilities. However, this is not enough. We also need the following property. In this case, if both properties hold, then these events are mutually independent. It means that there are no any dependence like between A3 and some combination of A1 and A2. If we have more events, then we have to test this kind of equality for any subset of our series of events. In machine learning, it is possible that we are interested in some variable we are going to predict, and we can use different features of our objects to predict it. And it is possible that we don't see any dependence between each of these features and the outcome. But if we unite all the features, we can use them to predict the outcome efficiently. This is the case which is similar to the case we discussed here, when there is no pairwise dependence, but we have dependence when we consider all events as a system. Now, we are ready to discuss a very important Bernoulli scheme. It is a probabilistic model that represents a series of independent trials. Each trial can result either in success or in failure. We will model this sequence by sequence of coin tossing. However, now this is not a fair coin, but some unbalanced coin, for which probability of head is different from probability of tail. To find probabilities of outcomes in this random experiment, we have to use independence condition. Now let us go to formulas. let us assume that we toss a coin 2 times. So n, the overall number of tossings, is equal to 2. In this case, we can consider 2 events. H1, first tossing gives head, and H2, second tossing gives head. Of course, in the first tossing and in the second tossing, we use the same coin. So the probability of H1 is the same as the probability of H2. We will denote this probability by P. In this experiment, we have 4 outcomes. We will denote them as usual by HH, HT, TH, and TT. However, in this case, when our coin is not necessarily fair, we cannot just say that probabilities of all of these outcomes are equal and equal to 1/4, because it is true only in case when probability of head is the same as probability of tail. However, we can use independence assumption to find probabilities of these outcomes. To do so, let us take into account the fact that H1 and H2 are independent, because the second tossing does not depend on the first tossing, and the first tossing does not depend on the second tossing. Our coin doesn't have any memory. Now we can use this assumption that H1 and H2 are independent, and we can use it to find probability of this outcome. We see that this outcome means that both of these events occurred. So probability of this outcome is the same as probability of intersection H1 and H2. Due to independence assumption, we can say that this probability equals to product of probabilities. Both of these probabilities are equal to P. So we have P times P, or P squared. Now we have probability of this outcome. Now let us find probability of some other event. For example, of this outcome, tail-tail. This outcome is the only outcome that belongs to the following event. Node H1 intersect with node H2, because if event H1 did not occur, so this event occurred, it means that at the first time we have tail, and here at the second tossing we also have tail. So we have to find probability of this event. It is easy to show, and it is a good exercise, that if these two events are independent, then these two events are also independent. It means that this probability equals to probability of node H1 times probability of node H2. Now, if probability of H1 equals to P, then probability of node H1 equals to 1 minus P. And here we also have 1 minus P. So the probability that we are interested is 1 minus P squared. In the same way, we can find probabilities of this outcome and this outcome. What is the probability of this outcome? In a similar way, we can show that it is a probability of head times probability of tail. So it equals to p times 1 minus p. This is the same probability for this outcome. Now we fully defined probability space for this experiment. We know all the outcomes and we know their probabilities. We used independency assumption to do this. Now we can consider a general case for arbitrary n. In this case, the set of all outcomes is a set of n-element sequences of heads and tails. So, how many outcomes we have in this case? The number of element in omega, the set of all outcomes, is 2 to the power n. Let us find probability of arbitrary outcome. For example, let us consider n equals to 5 and the outcome is head, head, tail, head, tail. In this outcome, we have 3 heads and 2 tails. It means that in the formula for probabilities, we will have 3 times factor p and 2 times factor 1 minus p. So probability of this thing equals to p times 1 minus p times 1 minus p. Of course, we are using independency assumption in this case. Moreover, we assume that our coin tossings are not only pairwise independent, but mutually independent, which is quite natural assumption, because even if we know, for example, the result of first 2 tossings, it gives us no new information about the result of the third tossings. So we can write this equality due to mutual independence. Now we can simplify this expression and get p to the power 3 times 1 minus p to the power 2. Here 3 is the number of heads here and 2 is number of tails here. Now consider the general case. Consider outcome O with m heads and n minus m tails. In this case, probability of this outcome equals to p to the power m times 1 minus p to the power n minus m. This factor corresponds to probability of heads, and this factor corresponds to probability of tails. Note that this probability does not depend on the order with which heads and tails occur. Only we are interested in the overall number of heads and number of tails. Thus, we fully defined Bernoulli scheme. So we described the probability space and described the probability of every outcome in this probability space. Bernoulli scheme is a very popular way to model processes in real life. In our life, we have to make a lot of decisions. For example, we have several schools, and we have to decide which school to visit. Or we have to choose which book to read at some particular moment of time. And these decisions can affect probabilities of various events. For example, of getting a particular job. We can use a probability theory to model, to some extent, this kind of relations between events, like choosing of school and getting a job. Let us consider one prominent example of this kind of reasoning, which is called law of total probability. Let us consider the following situation. We have a university with a 3-year educational program. And we are interested in some ability of the students of this program. For example, knowledge of calculus. We can consider the following random experiment. We pick a random student, and then we can consider the following events. First, the student can belong to first, second, or third years of education. This event is denoted by H1, and the same events can be denoted H2 and H3 for second and third years. So H2, H3, similarly. Then we are interested in knowledge of calculus. So event C is that student knows calculus. Now, assume that we know probabilities of these events. Assume that probability that the randomly chosen person is first-year student is 1/2. And for second year, the corresponding probability is 0.3. This probability is less than this one, for example, because some students were expelled. And probability of H3 is 0.2. Note also that a student cannot belong to 2 years at the same time. So HI and HJ does not intersect each other if I is not equal to J. We also say that we pick random student, and every student is either first year or second or third year. So at least one of these events have to occur. So we have the following thing. The union of all these 3 events is full probability space. It means that these events is a kind of alternative. We are choosing between one of 3, and we have to choose at least one, and we cannot choose 2. So it means that we have to choose exactly one. Now, assume that we know conditional probabilities of event C provided these alternatives. For example, probability of C provided that H1 equals to O.1. It means that probability that randomly chosen person from first year students knows calculus is 1/10. This is quite small because mostly no students of first year know calculus. But at the second year, this probability can be increased. Probability of C provided H2 can be O.8. And let us assume that probability of C provided H3 is O.7. Because at third year of education, some students already forgot everything that they knew about calculus. So we know the probability of that randomly chosen student of first year of education knows calculus, of second year, and of third year. What we want to do is to combine this information to get probability that simply randomly chosen person, randomly chosen student knows calculus. So we are interested in probability of this event C. How to do it? Let me show you the picture. Assume that this square is full probability space. And here this part is H1. Here is O.5. And this part is H2. Here we have O.3. And this part is H3, and here we have O.2. Now we have to take into account these probabilities. Probability of C, provided that H1 holds, is O.1. It means that out of this rectangle we have 1/10 that belongs to C. Out of this rectangle we have O.8, the corresponding conditional probability. It means that 80% of this rectangle belongs to C. And the same thing with the third rectangle. The union of these smaller rectangles is actually the event C. So we have here the height is O.8 and this height is O.7. Now we have to find the relative area of this figure related to the area of the whole square. This can be done pretty simple. We have to find areas of all these smaller rectangles and then sum them up. So if this figure, let me emphasize it, this figure is our event C. Now let us find probability of C. It equals to area of this rectangle, which is O.5 times O.1 plus probability of this rectangle, which is O.3 times O.8 plus probability of this rectangle, which is O.2 times O.7. So the answer is O.43. Now let us find the general formula that allows us to obtain results like this. Let us consider probability of C, and let us decompose this C into union of three separate events. Here, each of these events corresponds to corresponding rectangle here. We see that these events cannot intersect each other because H1 does not intersect H2 and so on. So we can write now we will use the definition of conditional probability to find these intersections. We know that probability of intersection can be rewritten in the following way. It is probability of one event times probability of another event conditional on the first one. So we have this product, and this product actually the same thing as these products, which is area of this small rectangle. In the same way, we can do it with other terms here. So we have this sum that use only the information that we have, probabilities of these events and conditional probability of C provided these events H1, H2, H3. We can rewrite it shorter using the summation sign. And this result gives us the law of total probability. It allows us to recover total probability of C out of its conditional probabilities provided these events. We proved it for three events, H1, H2, H3, but it is also possible to prove it in the same way for two such events or more than three. However, we have to take into account these conditions. These events are usually called hypotheses. They actually generate some kind of partition of all probability space into some non-overlapping areas. In other words, we have alternative. We have to choose exactly one of these hypotheses. Law of total probabilities allows us to find probability of C provided that we know these probabilities. It is interesting to consider an inverse question. Assume that we know that event C occurred. So assume that we know, for example, that randomly chosen person knows calculus. What is the probability, for example, that this person is from the first year? So it is interesting to find probability of hypothesis provided that these events hold. To find it, we have to use Bayes' rule that we will discuss later. So, Bayes' rule allows us to, in a sense, inverse these conditional probabilities. For example, let us find probability of H1 provided that C occurred. It means that we picked a random student and we found that this student knows calculus. What is the probability that this student is a first-year student? On one hand, we have a lot of first-year students, more than, for example, second-year students. On the other hand, most of the students don't know calculus due to this low probability. Of course, if a student knows calculus, it should increase the probability that this student is from second year or third year, and decrease probability that the student is from first year. But what is the exact value? Let us calculate it. Let us look at this picture again. To find this conditional probability, we have to answer the following question. What is the proportion between the area of intersection H1 and C, so this rectangle, and the whole C, so this thing. We can again use the same formula for intersection that relates probability of intersection with conditional probability. Now we can rewrite it in the following way. This is probability of C provided H1 times probability of H1. And we have to divide it by P of C. Let me recall that we found previously that probability of C equals to 0.43. Now we can find this probability. This conditional probability is 0.1 times this is called prior probability. It is 0.5 over 0.43. So we have this ratio, which is approximately 0.12. These probabilities are called prior probabilities for this hypothesis, and this probability is called posterior probability for hypothesis H1. This means that we find this probability provided that we observed that C occurred, and this fact that we know that C occurred gives us new information about probability of H1. We see that indeed it drastically decreases the probability of H1 from 0.5 here to 0.12 here. This is how Bayes' rule works, and it can be applied in different situations when we have to do this inverse. This is used in Bayesian statistics and in some branches of machine learning. Let us use Python to study conditional probabilities of events that are given as subsets of sample space. To do so, we first have to introduce the sample space itself, that is, the set of all outcomes. Let us consider an example when we toss a coin several times. The corresponding set of all outcomes is a set of all possible sequences of heads and tails. To create such a set, we can use itertools module that allows us to find a Cartesian product of some sets. To do so, we have to import itertools, and we will use function product, which is Cartesian product. And let me show you how it works. We can find list of product. For example, we have two sets or two lists. For example, 1, 2, and another is ABC. We see that this function product makes an iterator that is converted to list by this list function, and this list consists of several pairs of elements. In each pair, which is a two-element tuple, first element is from first list, and second element is from second list, and all possible combinations are enumerated. So let us assume that I want to toss a coin several times. For example, 3 times. This is number of coin tossings. Then I can create my sample space. Let me denote it by omega, and it is a set of a product of n copies of this list of 2 elements. So we can use option repeat, which creates a Cartesian product of several copies of the same list. So here omega is just this set, and we can check that all outcomes are included in this set. So as you see, the number of elements in this omega is 8, which is indeed the correct number. Now let us introduce several events. For example, we can introduce event A that corresponds to condition that at first tossings we have tail. So we can define these events, this set, using set comprehension. We just enumerate all items from our set omega. I denote one outcome by ohm that satisfy the condition that ohm of 0, so it is the result of the first tossing, is tail. So first tossing is tail. And we can introduce another event, for example, that we have exactly 2 tails. This can be done in the following way. Ohm count t equals to 2. So we can check outcomes that satisfy A's. So we see that we have 4 outcomes here, and we have 3 outcomes that satisfies B. Now we can find their probabilities, and we can find their conditional probability. To do so, let me introduce a couple of functions. First function calculates probability of some event x, and it works if we assume that all outcomes have the same probability. And in this case, a probability of x is just number of elements in x divided by number of elements in omega. And we can also introduce conditional probability of 2 events. So this is conditional probability of event X provided that Y occurred, and it can be calculated in a similar way. We just have to find a number of elements in their intersection, which is denoted by this ampersand, and divide it by number of elements in Y. So we have this thing, and now we can find some probabilities. For example, probability of event A is 1/2, which we expected, and the probability of event B is a little bit less. And we can also find conditional probability. For example, conditional probability of A provided that B happened. So if we know that the overall number of tails equals to 2, does it make it more probable for A, which is first tossing its tail, to be more probable or less probable? Let us check. We see that the corresponding conditional probability is 2/3, and it is higher than probability of A. It means that these events A and B are not independent. We actually can check it also by considering probability of their intersection. Probability of intersection, and comparing this probability with product of probabilities of A and B. Again, you see that these two numbers do not coincide, and it also means that these two events, A and B, are not independent of each other. So we can construct a function that checks is it true that two events are independent. We can do it in different ways. For example, in this way. Now let me introduce some event that is independent of A. For example, we can consider event C, for which we test is it true that at the second tossings we get head, and this can be done in the following way. Now we check, is it true that A and C are independent? And we see that the result is true. This approach allows us to find probabilities of events when they are given explicitly as subsets of sample space, or as a condition that allows us to find the corresponding subsets. But in practice, in most of cases, we will do a little bit different thing. We will simulate some random experiments with computer, and we will ask the computer, for example, to to give us some random value and use them to study properties of random variables. We will discuss random variables at the next week. During this week, we discussed conditional probability and independence of events. We discussed the definition of conditional probability, that is, probability of A provided that B occurred, equals to probability of their intersection, because they have to occur simultaneously, divide by probability of B, which is the probability of condition. And it is the probability of A provided B. If two events are independent, it means that probability of A provided B is the same as probability of A, or equivalent condition can be written as probability of B provided A equals to probability of B, or equivalently probability of their intersection equals to product of probabilities. In this case, events are independent. Sometimes we can use this definition to find some probabilities if we know in advance from some other considerations that two events are independent. Sometimes we have to prove that two events are independent by checking these conditions. We discussed the important law of total probability that allows us to find a total probability of some events when we know its conditional probabilities provided some hypothesis and the probabilities of these hypotheses. And we also discussed Bayes' theorem that allows us to find a probability of some hypothesis provided that event A occurred. The next week will be devoted to the notion of random variable. We need this notion to describe and model our data. Our data usually consists of different values related to different objects. For example, income of some person, or number of children in their family, or area of some house, or rent payment, and so on. And these values have some probabilistic nature, because if we have some data or some data set, this data set usually obtained during some random sampling. For example, we have a population of people and we sample random people from this population and ask them to fill in questionnaire and use this result as our data. So we need the notion of random variable to be able to model these values in our data. Basically, a random variable is a value that is determined by some random experiment. On the next week, we will discuss how to describe random variables and how to study them. In our course, we will study random variables. Random variable can be used to model some natural phenomena, and it is the main tool that we will use to study our data. But what is random variable? To answer this question, let us consider some casino. This is world-famous Casino de Monte Carlo. I have never been in this place, but I can imagine how it looks. Some well-dressed people make their bets on different games like roulette or blackjack. And this is a perfect example of some random variables. Indeed, consider roulette. You probably know how it looks like. There is a wheel with 37 sectors, and on each sector there is a number, and some sectors are red and some sectors are black, and there is a special sector which is called 0, and it is green. And people can make different bets. For example, one player can bet for a particular number, for example 23, and another player can bet, for example, for even or for red, and there are various other examples of bets. Consider Alice. Alice bets $100 on red. It means that If the small ball that spins inside this wheel stops in red sectors, then she wins, and her winning is $100. But in other case, if the ball stops in black sector, then she loses her $100. And there is a special case when balls stops at 0. In this case, she loses $50, half of her bet. When I described these rules, I didn't give you information on what will be exact payout of Alice after one spinning of the wheel. But you understand how this payout works in probabilistic terms. You can answer different probabilistic questions. For example, what is the probability that Alice wins some positive amount of money? You can find it by calculation. Alice payout is an example of random variable, that is a variable which value depends on the result of some random experiment. In this case, random experiment is the spinning of this roulette. This is actually informal definition of the notion of random variable. Random variable denotes some value that depends on the result of some random experiment. So, to define a random variable, we have to describe random experiment in some way. Of course, random variables are not limited to gambling. We will use them to model a lot of different natural phenomena. For example, how many people will finish this course? I don't know exactly, but I can propose some model that will involve random variable for this number. What will be your final grade? It is also a kind of random variable because we don't know in advance what will be this value. What will be the price of Bitcoin tomorrow? A lot of people want to know this value, but nobody can. It is an example of random variable as well. What will be opening weekend box office for a particular new film? Again, a lot of people interested in this value, and nobody knows the exact value before we conduct our random experiment, before we perform this film for the first weekend and get the actual value. So, let us discuss what will we study at the lesson. First of all, we consider some more examples of random variables, just to have some examples to begin with. Then we will discuss that there are two kinds of random variables that will be discussed in our course. Discrete random variables and continuous random variables. During this week, we will discuss discrete random variables. Then we will discuss how to define and describe random variables and how we can visualize them. We will also study some important distributions of random variables, like binomial distribution. We will discuss properties of random variables like expected value and variance. And finally, we will use Python to generate and study random variables. So, let us begin. Random variable is a universal model of some quantity that we know with some level uncertainty. And we will assume that our data are realization of some random variables. So, to study data, we have to study random variables first. We will do it using a very simple examples. First, let us consider a random experiment that we discussed previously, coin tossing. Let us assume that we have a fair coin and we toss it several times. Then we can consider different random variables associated with this experiment. For example, we can count how many heads we get during this tossing, or how many tails, or something else. But let us begin with the number of heads. So, x is a number of heads that we obtain during this tossing. Let us consider first the simplest case when n equals to 1. So we have only one tossing. Then we can have either 0 heads or 1 head. And we can draw the following table that relates outcome of the random experiment and values of our random variable. For one coin tossing, we have exactly two outcomes. It can be either head or tail. And the corresponding value of x have to be 1 here and 0 here. If we toss one coin and we have head, then the number of heads is 1. And if we toss one coin and we have tail, then the number of heads equals to 0. So this is pretty simple. Consider a little bit more interesting example when the number of tossings equals to 2. How many outcomes do we have? We have 4 outcomes. First head-head, then head-tail, then tail-head, finally tail-tail. We can find the value of x for each of these possible outcomes. If the outcome is head-head, then we have 2 heads and the value of x is 2. If we have head-tail or tail-head, then we have only 1 head during our sequence of tossing. So for both outcomes, the value of x equals to 1. And finally, if in both tossings we have tail, then we have 0 heads and value of x is 0. In a similar way, we can define the corresponding number of heads for n equals to 3 or some other number. We can also consider a non-fair coin, but a coin that gives head with some probability p. This is a very well-known Bernoulli distribution that we will discuss later. But now let us consider different random experiment and associate some random variables with it. For example, let us instead of coin tossing consider dice tossing. For one dice, if we toss it one time, we have 6 possible outcomes. And we can associate some random variable with these outcomes. For example, we can consider the square of number of points that we get on the dice. I will denote outcomes by the corresponding pictures. And let us consider random variable y, which is the square of points. Then if we have 1 point, then the value of y equals to 1. If we have 2 points, the value of y is 4, and so on. 9 here, 16 here, 25 here, and 36 here. In these examples, the value of random variable is integer number. But in fact, it is possible to consider random variable with non-integer values. Let us consider an example of such random variable. Again, first we have to introduce a random experiment. For example, let us assume that I have 3 coins. One coin is $1 coin, another coin is $half coin, and the third coin is a quarter. Now, let me assume that my random experiment is the following. I get randomly 2 of these 3 coins, and the value of random variable is the amount of money that is in these coins. So, for example, if I get an outcome that I choose this coin and this coin, then the value of random variable that I will denote by z will be a sum of these amounts. So it is 1.5. Now we can consider different outcome that we choose, for example, this coin and this coin. The corresponding value of z equals to 1.25. And finally, the third possible outcome is that we choose this coin and this coin. And the value of z is 0.75. So this gives us another example of random variable. Now let us pass to the mathematical definition of random variable. Let us define what random variable is from a mathematical point of view. In this example, when x is the number of heads into tossing, we see that for each outcome we have the corresponding value of x. Mathematically, it means that we defined a function on the set of all outcomes. In this case, this function can be described by a phrase number of heads. But from a mathematical point of view, this function is described just by this set of numbers. And we can introduce different random variable by specifying different numbers here. The only thing that we have to take into account is that for each outcome here, we have to specify exactly one value of the corresponding random variable. So let us write down the definition formally. Let omega be sample space, that means the space of all outcomes in some random experiment. To define a random experiment, we also have to define some probability. For example, in our simple cases, when omega is just a finite set of all possible outcomes, then to define probability, we can define a probability of each outcome. In more complex cases, we have to do it in different way, but we will discuss it later. Now, we say that we defined a random variable if we defined a function from omega to real numbers. If we conduct random experiment, it means that we choose randomly an outcome from this set. In this case, if omega small is the result of random experiment, so omega is element of omega capital, then we can find the value of x of this omega. So x of omega is the value of function x capital of this omega small. It is the value of corresponding random variable. If we conduct the same experiment several times, for each time we have its own omega small, its own outcome, and its own value of random variable. In this case, we can say that we sample our random variable, and during this sample we get just a sequence of some numbers. This sequence is called a sample, from our random variable. During our analysis, we'll assume that our data is sampled from some system of random variables. Now, let us discuss how can we describe random variables in a convenient way. We can describe random variable using definition. So for each outcome, to define which value our random variable take for this particular outcome. However, this can be too complex to do it, and it is possible to use a more compact way to describe random variable. To do so, we have to introduce the notion of probability distribution. Let us return again to an example where x is the number of heads in two tossings. We see that we can ask some question. For example, what is the probability that x equals to 0? And we can answer these questions using this table. We know that in our case, when a coin is fair, the probability of each outcome is 1/4. If we ask what is the probability that x equals to 0, it means that we are interested in the probability of event that satisfies this condition. The only outcome that belongs to this event is this one, tail-tail. So we can write that probability that x equals to 0, it is a shorthand notation for the following event. It is a probability of event that consists of all outcomes for which this condition holds. So we basically just have to look at this table and select all rows for which value of x is given. So the only row that we have is this row and this outcome. So this is probability of tail-tail, and this probability equals to 1/4. In the same way, we can ask what is the probability that x equals to 1? How do you think, what is the answer? Let us find. Probability that x equals to 1 is the same thing as probability of event that consists of outcomes for which this condition holds. So for these two outcomes. So we have probability of event head-tail, tail-head. The probability of this event equals to 2/4 because we have two equally probable outcomes. In the same way, we can answer the question, what is the probability that x equals to 2? This probability, as you can easily find, equals to 1/4. Now we can write down the following table. In the first row, we will write all possible values that our random variable x capital can take. We have exactly three values, 0, 1, and 2. And in the second row, we can write down the probability of the corresponding event that our random variable take the corresponding value. So here we write 1/4. This is this 1/4. Here we will write 1/2. This is this 1/2. And here we will write 1/4. This is this 1/4. Now we have this table that is a different way to describe the same random variable as here. As you can see, we can use this table to answer some probabilistic question about x. For example, if I want to ask what is the probability that x is greater than or equal to 1. Let us find it using this table only. Again, this is shorthand notation for event that consists of all outcomes that satisfy this condition. So we can use this table to find this probability, but instead of that, we will use this table. If x is greater than or equal to 1, we see from this table that it means that x can be either 1 or 2. No other options available. So we can write that this probability is equal to probability of the following event. We see that these two events are disjoint, because if x equals to 1, it cannot be equal to 2. It means that this probability can be defined as a sum of two probabilities. And both of these probabilities are written in this table. So we see that this term equals to 1/2, and this term equals to 1/4. So finally, this sum equals to 3/4. Now we see that we can use this table to answer any probabilistic question about random variable x. This table is called distribution of x. Now let us define the general notion of probability distribution. Let us consider some random variable x that take only a finite number of possible values. We'll denote these values by small letter x with indices x1, x2, and so on, xn. To draw this kind of table, we have to specify with which probability each of these values is taken. So we have to specify a sequence of numbers that we will denote by p1, p2, and so on, pn. So we have probability that x capital takes value xg is pg, and g here is from 1 to n. This pair of two sequences is called distribution of random variable x. It is easy to see that not arbitrary numbers can serve as p's in this distribution. Each of these numbers is the probability of some event, and it means that it has to be non-negative number. Also, the random variable x can take some of these values. It means that the probability that at least one of these numbers will be taken have to be equal to 1. It means that the sum of these values have to be equal to 1. And vice versa. If we have a pair of such sequences and values p1, p2, and so on, pn satisfy these two properties, then we can introduce a random variable that takes these values with given probabilities. It means that this pair of values and probabilities is a distribution of the corresponding random variable. So formally, we say that we have probability distribution if we have this pair of sequences such that these properties satisfied. It holds in case when random variable take only finite number of possible values. It is possible to generalize the notion of probability distribution to the case when the number of possible values is infinite, and we will discuss it later. Now I just want to stress that probability distribution is a good way to think about random variables. In different cases, we will specify random variable with its distribution. Let me also introduce another notion that is useful tool to describe the distribution in mathematically convenient way. This thing is called probability mass function. For a random variable that takes only finite number of values, probability mass function is the following function. We will denote it by PMF, probability mass function of random variable x is just a function that is probability that random variable x takes value x small. This is called probability mass function. Let us find probability mass function for a random variable in this example. We will draw the graph of this probability mass function. The only values for which probability mass function is non-zero is exactly those values that our random variable can take. So we have 3 points for which the corresponding probability is non-zero. The first point is 0, and the corresponding probability is 1/4. And the second point is 1. and the corresponding probability is 1/2. And finally, we have value 2, and the corresponding probability is again 1/4. So the graph of our function consists of these points, and in all other points we have the value of the corresponding probability mass function to be 0. So the graph looks like this one. It will be useful for us to use probability mass function as a way to visualize probability distributions. For example, here we see that probability of getting value 1 is twice as large as probability of getting value 0. Now we will use these ways to describe probability distributions to consider some other random variables. Now, let us discuss the very important binomial distribution. Binomial distribution is a distribution of random variable that counts the number of heads in n tossings of a coin that is not necessarily fair. So our random experiment is to toss n times a coin that not necessarily fair. We will denote the probability of head as p. And so probability of tail is 1 minus p. Now x is number of heads. We can think about x in the following way. Let us assume that we have a sequence of independent trials. Each trial can result either in success or in failure. If we identify success with heads and we say that the probability of success is p, then x is number of successful trials. And this is a rather general model for different natural phenomena. So now let us find the distribution of x. It is easier to begin with some simple example. Let us assume that n equals to 5. Let us find probability that x equals to 0. If we have 0 head, then it means that we have 5 tails in a row. So the probability of this event is probability of the following outcome. Tail, 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 tail. As the probability of each tail is 1 minus p, and all these tails are independent of each other, we can say that the probability of this outcome is 1 minus p to the power 5. In the same way, we can find, for example, probability that x equals to 1. But it becomes a little bit more complicated, because in this case this one head can be placed into one of these possible 5 places. And in this case, we have not one outcome, but 5 different outcomes. However, as we discussed before, the probability of each outcome of this kind does not depend on the actual place of this head. It can be found in the following way. Probability of, for example, head, tail, 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 tail equals to p times 1 minus p to the power 4. Here we can write p to the power 1. Here 1 is the number of heads and 4 is the number of tails. And we have the same number, the same probability for each of these outcomes, because this probability does not depend on the place of this h. So the overall probability here equals to 5, the number of outcomes, times this thing. For other values of x, things become more complicated, and we have to use binomial coefficient to find the number of appropriate outcomes. Indeed, for example, what is the probability that x equals to 2? Again, we have to find a probability of one outcome that satisfies this condition. For example, of outcome like head, tail, tail. This probability equals to p to the number of 2 times 1 minus p to the number of 3. Here this 2 is the number of heads and this 3 is number of these tails. Now we have to find the number of all outcomes for which number of heads equal to 2. From combinatorics, you can remember that this number is denoted by the following thing. This is binomial coefficient 5 choose 2. And we have to multiply this binomial coefficient by this probability. By the way, 5 is binomial coefficient 5 choose 1, because it is exactly the number of ways to choose one element out from 5. Now, let us consider the general case. Probability that x equals to some number k equals to the following thing. This is binomial coefficient n choose k times p to the power k times 1 minus p to the power n minus k. Here this value is number of outcomes with exactly k heads. Indeed, this number is the number of ways to choose k elements out of n. If we have n tossings, then it means that we have n places and in k of these places we have to put letter h, and the rest will be t. So we have to choose k places out of n places. So this can be done with this number of ways. And each of these outcome corresponds to this probability. These outcomes are mutually disjoint, so the probability that any of these outcomes take place is this product. Here in this formula, k is arbitrary integer number from 0 to n. Now, if random variable has this distribution, we will say that this random variable is binomially distributed with parameters n and p. We will write it in the following way. X is distributed as binomial distribution with parameters n, number of trials, and p, probability of successes. In this way, we described a family of important distributions. We will use them in future. Probability distribution gives us a lot of information about random variable. But sometimes we want to answer the following question. What value our random variable takes on average? What does it mean on average? You know that if you have some finite number of values, we can find the average of these values by finding their sum and dividing by the number of these values. But for random variables, this method doesn't work in general, because we have to take into account that some values of random variable are taken with large probabilities and other values are taken with low probabilities. It is natural that those values with large probabilities will contribute more to the average value. The easiest way to think about average of random variable is to think about average win, average payout in some kind of lottery. Let us consider an example of this kind. The notion that we will discuss is expected value of a random variable. And let us begin with a simple example. Let us assume that Bob plays the following lottery. His payout will be denoted by X capital. It is a random variable, and we have only two possible values for X. Either Bob can win $5, and this happens with a probability 0.1, 1/10, or Bob can lose $1, and this happens with probability 0.9, 9/10. The question we are interested in, what is an average payout of Bob? To find this average payout, let us assume that Bob plays a lottery many times. Let us assume that Bob plays, for example, 10,000 times. How many times he wins out of this 10,000? Approximately, the number of wins equals to the number of plays by the probability of winning. So we can say that approximately Bob wins about 1000 times O.1, it equals to 1000. 10,000 times O.1 is equal to 1000. And how many times he loses? If he wins with probability O.1 and loses with probability O.9, to find the number of losses, we have to multiply 10,000 by O.9, and this is 9,000. Of course, these numbers are approximations. We don't know exactly how many times he wins. It's possible that he wins 1002 times or 999, but it is almost impossible to expect that he wins, for example, 2000 times with, if this probability is given. So let us assume now that these numbers are correct. In this case, his payout can be found in the following way. For winnings, to find the payout, we have to multiply this 1000 by his payout per one game. It is 5, and we have 5,000. And for these losses, we have to multiply this number by this value and get negative 9,000. Now, to find the overall payout, we have to find a sum of these two numbers. It equals to negative 4,000. Now, if we are interested in average payout per one game, we have to divide this value, his payout per 10,000 games, by the number of games. And we get minus O.4. So, basically it means that per every game, Bob loses 40 cents by playing in this lottery. We can find this value in a little bit different way. Let me rewrite the formulas that we have here in one line. So we had this 5,000 that is found by this multiplication, and this 1,000 is found by this multiplication. So we can write it in the following way. In a similar way, we can think about this negative 9,000 as the product of this 9,000 and this negative 1. And this 9,000 is this product. So let me rewrite it once again. Plus 10,000 times 0.9 times negative 1. This thing is this negative 4,000. So this is payout per 10,000 games. To find payout per one game, we have to divide this thing by 10,000. Now we see that 10,000 in numerator and denominator can be cancelled. And we have the following formula. We see that in this formula we have probabilities. This thing is a probability of this value, and this thing is probability of this value. So, to find the expected payout, we had to multiply each value by the corresponding probability and make a summation. You see that in this way we found average in probabilistic sense, average payout per one game. From practical point of view, it doesn't matter how we analyze our game. If we know that Bob plays a lot of games, we can either assume that he plays this lottery every time, or we can assume that he merely gives to the lottery organizer this amount of money every game. And the result after 10,000 games will be approximately the same. This is what we mean when we say that this is average payout per one game. In the same way, we can define an expected value of any random variable. Let us assume that we have a random variable and we know its distribution. So we have values x1 and so on xn and corresponding probabilities p1 and so on pn. So we basically have a table like this. Here are possible values x, and here are probability that our random variable x capital takes the value x small. Now, to find the expected value of this random variable, we have to make a similar thing. We have to multiply these values by the corresponding probabilities and find a sum. Expected value, it is written like this one. Expected value of x is x1 times p1 plus x2 times p2 plus and so on plus xn times pn. The same as xk pk. this thing is by definition called expected value of random variable x. Now let us find expected values of some random variables that we discussed before. After we discussed the definition of expected value, let us practicize a little bit. Remember Alice, who bets $100 on red in roulette game. Let us find her expected payout. Let me recall the rules. In roulette, we have 37 sectors, 37 numbers. And out of these 37 numbers, we have 18 red, 18 black, and 1 zero. 0 is neither red nor black. It is actually green. So overall number of sectors is 37. And if Alice bets $100 on red, then her payouts will be as following. If the ball stops at red sector, then Alice wins her bet. So her payout is $100. If the final sector is black, then Alice loses her bet. So her payout is negative $100. And finally, if 0 is the result of our game, then Alice loses half of her bet. So her payout is negative $50. Now, let us find the expected value, expected payout. To make it possible, we have to find the probabilities of all these outcomes. So, let us write down the probabilities. What is the probability to win? We have 18 sectors out of 37. So the probability is 18 over 37. In the same way, the probability to lose $100 is the same, 18 over 37. Here, the probability to get 0 is just 1 over 37. Now, if we consider this table as a distribution of a random variable, which is Alice's payout, then we can find the expected value of this random variable. To do so, we have to multiply payouts by their respective probabilities and make a summation. What is the expected value of x? Now let us do the math. We have to multiply 100 times 18 out of 37 plus negative 100 times 18 over 37 and plus negative 15 times 1 over 37. We see from this formula that these two terms will cancel each other because they are equivalent up to this sign. So the expected value is given just by this formula. And if you find the value of this number, we will get approximately negative 1.35. Now we see that every time when Alice bets $100 on red, she loses on average $1.35. This is not so large amount of money, probably, but it is important that it is negative amount. So the more Alice plays this game, the more she loses on average. This is what makes casinos profitable. Now, let me show you another way how we can calculate this expected value. Instead of considering this table, the table of distribution of this random variable x, we can return to the definition of random variable and consider our sample space, probability of outcomes, and the value that is associated with every outcome. Let me show you how to do it in this way. Let us recall that the sample space in case of roulette consists of 37 outcomes. We will denote them just by the corresponding numbers 0, 1, 2, 3, and so on, 36. And with each value that we have here, we have the corresponding value of our random variable. For example, what is the x of 0? 0 is neither red nor black, so the value of x here equals to negative 50. You can find a picture of roulette and find what is the value of x of all other numbers. What is x of 1? If you find a picture of roulette, you will find that 1 is red. So it means that x of 1 is 100. Because 1 is red. In the same way, x of 2 equals to negative 100, because 2 is black. And so on. Now, we can write another definition for expected value, another formula. Expected value of random variable x is sum over all outcomes of our sample space of the following product: probability of this particular outcome times value of random variable at this outcome. This is an alternative way to define the notion of expected value. And it works exactly in the same way as the definition that we discussed before. Let us check it in this example. Here, to make this summation, we have to write down 37 terms that correspond to 37 outcomes here. Of course, most of them will be equal to each other. So, let us begin, for example, with red numbers. The probability of each outcome is 1 over 37. So, we have the following. Let us consider first outcomes that corresponds to winning. So we have 1 over 37, which is the probability of outcome, times 100, which is the value of random variable. And we have 18 summands like this one. In the same way, we can count outcomes that corresponds to this case. We have again 1 over 37 times negative 100, and so on. Again, we have 18 times. And the only outcome that is remain is 0. The probability again 1 over 37. And the corresponding value is negative 50. Again, we see that these terms and these terms cancel each other. And what we get is this term, which equals to this term and this result. So this formula gives us a new way to define the expected value, which is equivalent to the alt one. We will use this definition when we will discuss some properties of expected value, like expected value of sum of two random variables. But now, let us discuss why expected value of random variable is so important in machine learning. One of the basic problems in machine learning is prediction problem. We have some information, we know something, and we want to use this information to predict some quantity that we don't know. Let us consider an example. Let us assume that we are a cafe and we sell pancakes. What we are interested in is how many pancakes should we prepare. It is determined by the demand. How many pancakes could we sell at a particular day? Of course, this is a random value because on different days we have different clients and they can be, some of them can be hungry and some of them can be non-hungry and some of them like pancakes and so on. So we have to use random variables to model this demand. And what we want is to predict this demand in some way. What is the best way to predict the value of this random variable? So, let us assume that x is our random variable, which is demand on pancakes. How many pancakes can we sell at a particular day? And we want to predict the value of this random variable. Let us denote our prediction by x hat. Let us assume that we choose this prediction once and forever. How can we measure the quality of our prediction? Of course, we have to consider the difference between the prediction and the actual demand at a particular day. This difference can be either positive or negative, but both is bad for us. For example, if we underestimate the demand, it means that we don't have pancakes, and we have some clients who want pancakes but doesn't have them, and it is bad for us because we lose some money on these clients. On the other hand, if we prepared more pancakes that we can sell, then it means that we again lose money because we just have these pancakes and nobody wants to buy them, and we have to throw them away. Even more, in some cases, it is a good idea to consider not this difference as our loss, but a score of this difference. For example, if we didn't prepare enough pancakes, we lose some money because we cannot sell the pancakes to the people who want them. And also these people can become angry, and they can give us bad marks on some websites and so on. So it is a good idea sometimes to consider our penalty as to be square of our error. This is actually a popular loss function in machine learning, which is called squared error. Look at this formula. We have x here. X is a random variable. So the whole formula defines a new random variable. At different days, we will have different value of this loss. For example, at one day, our prediction can be good if we are lucky enough, and on the other day, for example, we have a demand which is much larger than we predicted, just due to chance, and we have large value of this loss. What we usually want is to make our predictions good at average. It means that we have to find an expected value of this loss. Now, this value is not a random variable because we have expected value here. This is just a number that depends on x hat. Let me denote this number as L of x hat. L stands for loss. Now, our goal is to minimize this function L of variable x hat by choosing appropriate x hat. How can we find such optimal x hat? Let us use calculus to do it. First of all, let us consider the distribution of random variable x. We assume that x takes values x1, x2, and so on, xn, with probabilities p1, p2, and so on, pn. However, we are interested not in the random variable x itself, but we are interested in our squared error loss. And for each value of x, squared error loss is calculated according to those formula. So let us find the distribution for squared error loss. It means that we just have to substitute the corresponding value here instead of x capital and get the following. So, for example, when x takes value x1, and this happens with probability p1, then our squared error loss takes value x1 minus x hat, and we have to take a square of this. And the same thing happens for all other possible values of x capital. Now, we can find expected value of this thing, so our L of x hat. To do so, we have to get these values, multiply them by these probabilities, and make a summation. Now, we want to minimize this function with respect to this variable x hat. As we know from calculus, to find minimum or maximum of some function, we can use derivative. So let us find the derivative of this expression. To find the derivative of sum, we have to find a derivative of each component of this sum. So we have the following. Now, this pi is a constant, so we can move it out of the derivative sign. To find a derivative of this thing, we can use the well-known rules and get the following. This is sum of two we have to put a negative sign here according to the chain rule, but it is not important now. And we have to multiply this by pi. So this is our derivative. We see that this function is actually a quadratic function of x hat. And the corresponding graph is parabola. And at the only point where the derivative is equal to 0, we have a minimum value of this function. So we have to find the value where this expression is 0. Let us do it. First of all, let us get rid of this 2 and this negative sign, because they are just constant, and we can divide this equation by the constant. So we have the following. Sum now we can expand this sum. In this sum, x hat is a constant, and we can move it out of the summation sign. And we also move this term to the right-hand side of the equation. Here we see the summation of all possible values pi. We know that this sum have to be equal to 1. Here we see the summation of products of values that our random variable x can take by the corresponding probabilities. So it is the expected value of x. Now we see that the optimal x hat equals to the expected value of x. This is a really important result. If you want to predict the value of random variable and you have squared error loss, then you can choose expected value of this variable as your prediction. We will see in the future that if we choose a different loss, we will get a different optimal value. But squared error loss is very popular due to good mathematical properties. So this is the first and simplest example of solving of prediction problem. Unfortunately, all this story is purely imaginary, because to find the expected value of random variable, we have to know its distribution. In reality, we usually don't have a distribution of random variable that we are interested in. We have only some data that are sampled from this random variable. However, this information about the importance of expected value gives us some hints on what to do in the general case. To measure how far a random variable deviates from its expected value, we will use variance. Let us return to an example about Bob, who plays lottery and bets $1 in this lottery and can win $5. So our lottery was defined as the following. With probability 1/10, Bob wins $5. And with the remaining probability, Bob loses $1. I will denote Bob's payout as XB. Let me recall that the expected value of XB equals to negative 0.4. Now the question is, how far the value of XB from its expected value? So we are interested in the difference between XB and expected value of XB. Again, as in previous example, we can find the distribution of this random variable. To do so, we have to add a new row to this table, XB minus expected value of XB. For example, when XB takes value 5, this value takes value 5 minus negative 0.4. It means it is 5.4. What should I write here? If XB takes value negative 1, then this thing takes value negative 0.6, because it is negative 1 minus negative 0.4. So we see that this difference is again a random variable. We are interested in how far xb differs from its expected value on average. Probably you want to put expected value here. You can use this table to find this expected value. What is the answer? Indeed, the answer is 0. We see that this difference can be either positive or negative. And when we multiply these numbers by these probabilities, we will have 0 because positive deviations will exactly cancel out the negative deviations. So we want to make positive and negative deviations to be of the same sign, so to kill the negative sign here. We can do it in different ways. For example, we can consider absolute value of this difference. But mathematically more convenient to use not absolute value, but a square. So currently we are interested in the following thing: expected value of square of difference between the variable xb and its expected value. This thing. This thing is called variance of xb by definition. Let us find variance of xb in this case. To do so, we have to find squares of these numbers. We have 29.16 here, and we have 0.36 here, and then we have to multiply these numbers by these numbers, this number by this number, and make a summation. So in this case we have and the answer is 3.24. You probably have to use calculator to check these calculations, but I believe that they are true. So this number gives us what we want. These numbers show the average deviation of the value of xb from its expected value squared. This thing is actually the same as we discussed before when we discussed squared error. If we use expected value of xb as a prediction of xb, then this expected value is just an expected value of squared error. It is, in a sense, the best possible squared error that we can get. Let us give a general definition. If we have some random variable x, its variance which is usually denoted by var x, is the expected value of the difference between x and expected value of x squared. We will use variance to distinguish between random variables which values are close to their expected value, so their range is narrow, and variables which range is large in probabilistic sense. It means that On average, they take values that are far from the expected value. So far, we considered only random variables with a finite number of possible values. However, it is possible that we deal with some phenomena in which the corresponding variable can take infinite number of values. This is also possible to consider. Again, we begin with a simple example. Let us return to our coin tossing experiment. But now, let us assume that we toss a coin not a fixed number of times, but we toss the coin until we see first head. So, our experiment: toss a fair, for simplicity, coin until first head. So, I basically toss a coin. If it's head, it's over. If it's tail, I toss this coin again. If it's head, it's over. If it's tail, I continue. And so on, until I have a head. Sooner or later, I will have a head. It is virtually impossible to get an infinite sequence of tails, at least if my coin is fair. So I can introduce a random variable, x, which is number of tossing until first head, including the head. Let us try to find a distribution of this variable. To find the distribution, we first have to say which values this random variable can take. It is obvious that x can take any positive integer value. Let us find the corresponding probabilities. What is the probability that x equals to 1? It means that we have head at the first tossing. The probability of this event is 1/2. What is the probability that x equals to 2? We can consider the following diagram. At first tossing, we can get either head with probability 1/2 or tail with probability 1/2. If it's head, then it's over. But if it's tail, then we have second tossing. And again, we can get head at the second tossing or tail. And again, the probabilities are 1/2, 1/2. So, to get this head means that the x equals to 2, because we have 2 tossings before the first head. The probability of this event is 1/4. And so on. We can continue this tree in the following way. And at every step, the probability of the corresponding event will be equal to 1/2 to the corresponding power. For example, for x equals to 3, the corresponding probability is 1 over 8, which is 1/2 to the power 3, and so on. For value k, we have here probability 1/2 to the power k. Now we have to check that these probabilities sum up to 1. And it is rather easy because it is a geometric progression. 1/2 plus 1/4 plus 1/8 plus and so on plus 1/2 to the power k plus and so on. This is actually 1, which we can simply illustrate by the following picture. If we have a square, and here we have 1/2 of this square, and this is 1/4 of the square, and this is 1/8 of the square, and so on. If we divide the rest part by 2, then we have the following term in this sum. And it follows immediately from this picture that the overall sum equals to 1. So we see that these numbers define probability distribution, even despite the fact that we have infinite number of them. Now let us give some definitions. So if x is a discrete random variable, then two possibilities can take place. Either x takes only a finite number of distinct values, this is the case that we considered mostly during this lecture. And in this case, the corresponding probability distribution is a finite set of values and their probabilities. But it is also possible that x takes not finite but infinite number of values. If we discuss discrete random variables, infinite means countable. It means that we have a kind of infinite sequence of possible values. In this case, the distribution is given by a pair of two infinite sequences of values and probabilities. Here we need that the finite sum of this P1, P2, and so on, Pn, to be equal to 1. Here we need the same from the infinite sum of these values, just like in the example before when we considered geometric progression. In both of cases, Pi should be greater than or equal to 0 for every I. Note that we can easily extend the definition of expected value to this case. Recall that in this case, expected value of variable x is a finite sum of this kind. Value times probability. And here the formula is the same. We just replace finite sum with infinite sum, just like this. Note that in contrast with finite sums, infinite sum can be non-existent. So, for random variables with infinite number of values, it is possible that expected value is non-existent. Let us discuss an interesting example of random variable that doesn't have expected value. Consider the following game. I have a fair coin. I toss this coin. If I have head, I give you $1. If I have tail, I toss it again, and if I have head, I give you $2. If I have tail, I toss it again. Now, if I have head, I give you $4. And so on. Every time I have a tail, I double my payout to you. Would you like to play this game? Probably yes. But the more interesting question is, how much money do you want to give me for the opportunity to play this game with me? Let us try to find it mathematically. This game is called St. Petersburg paradox. Let us describe it formally. Again, we have a sequence of coin tossing, and on first tossing, it is possible to get a head or tail, and if we have head, then the value of our random variable is 1. This is my payout to you. X is payout. And the probability of this head is 1/2. In case of tail, which happens with probability 1/2, we continue the game, and now we again have two possibilities. If we have head, then X equals to 2, and if we have tail, we continue. Again, we can have head. In this case, X equals to 2 to the power 2, which is 4, or tail, and so on. So the probabilities here are 1/2, 1/2, 1/2, 1/2. So our random variable have the following distribution. We have 1 with probability 1/2, two with probability 1/4, which is 1/2 to the power 2, 4 with probability 1/2 to the power 3, and so on. So basically the probability that X equals to 2 to the power k equals to 1 over 2 to the power k plus 1. Here we have 1 which is 2 to the power 0, and here the probability 1/2. And at every step the corresponding probability is multiplied by 1/2, and the payout is multiplied by 2. Now let us return to the question, how much money you want to pay me for the opportunity to play this game. To answer this question, let us find the expected value of this random variable. This expected value is your expected payout. It is obvious that you will play this game with me if the price of the ticket is lower than your expected payout, right? Let us find. Expected value of x, according to definition, is a sum of possible values that x can take, multiplied by the corresponding probabilities. Due to this definition, x can take values of form 2 to the power k. So we have to find a sum for k from 0 to infinity of these things. This is probability, multiplied by this thing, which is the value. We can simplify it, because this 2 to the power k and this 2 to the power k plus 1 cancel each other, and so we have some. So we can write it as 1/2. So we have sum of infinite number of values 1/2. This infinite sum is exactly infinity. So you see that your expected payout is infinitely large. You probably want to pay any amount of money to be able to play this game with me. However, the real persons do not behave in this way. In experiments, people do not want to pay a large amounts of money to play this game. So this can be explained in different ways, using some psychological arguments or utility theory. However, this is out of the scope of our lecture. For us, this is just an interesting example of random variable that do not have expected value. However, in most of cases, we will consider random variables that have expected values. Let us discuss a couple of distributions of random variables with infinite number of possible values that can be useful in practice. The first one is geometric distribution, which is a direct generalization of the distribution that we discussed before, a number of coin tossing before first head. So, in geometric distribution, we toss a coin, but now this coin is not fair, probably.